Swayam Prabha. Digital India. Educated India.
Good afternoon, everybody. I welcome you to this live session of the course NPTEL course Flow Through Porous Media. I understand you have gone through by now the flow equations. You have gone through by now the dispersion, which is a very important aspect of flow through porous media. And I have received a few questions, very good questions, mostly from some selected students, not a very wide participation, but those are very pertinent questions. And I will wait maybe for 1 or 2 minutes. I'll have some general discussion and I'm waiting for 1 or 2 minutes if more question shows up in the chat box. And then I will start discussing those. Let me open a page because that will help me to write things. Then it becomes easier for me. What I see is that there are few questions on this dispersion, and then there are few questions on use of Bernoulli's equation. Of course, there are a few questions on how we define tau when we try to relate flow through a capillary and then extend that to flow through porous medium. So for that, we first try to define what is friction factor. So there are a few questions on those. So what I note here, first of all, you must have noticed by now that we have considered dispersion as cumulative effect of molecular diffusion, I should say molecular diffusion, and then axial convection or advection, you call it, yes. So advection, let me call this advection. So we have now what we have noticed there is that we have defined first of all a DCT term, dispersion in capillary tube. So DCT term, which we have defined as R square, where R is the radius of the capillary, V square by 48D, where D is the molecular diffusion coefficient. This sort of dispersion comes into play because we have a parabolic velocity profile inside the capillary. So the step change that I impose, the step will not, I thought that as if it is a plug flow, the step would have traveled just like a plug, just like a straight uniform front. But because of this parabolic nature of the velocity profile, the step itself would be twisted like this. So you will end up with not mere diffusion across a front. This side you have higher concentration, this side you are having zero concentration, and as if there is molecular diffusion happening from higher concentration to lower concentration. This was our conceptualized this was our conceptual understanding of movement of a front, movement of a plug through a capillary. But since we are considering parabolic velocity profile, so as a result we have the front also stretched like this, so that it is not merely molecular diffusion across this phase, rather it is molecular diffusion in radial direction, molecular diffusion in radial direction. And since I am collecting the samples at the outlet in the form of strips, so it is an effect of axial, effect of advection also, because if the V increases, this would change the shape of the profile. So this is going to be the, this is going to replace the diffusion term as we have studied in case of diffusion of a spot of dye in a static pool of liquid, but that term had to be changed like this. This is one point. The second point that we must work on is that the velocity term that was there, the velocity term appeared in error function of, so somewhere we had z, that z has to be replaced by z minus u bar t. That was the, because we have continuously our center, or continuously our front position is changing, so we have to work with a moving coordinate system, so that also has to be accounted. So when we change this, this becomes a modified coefficient. Instead of molecular diffusion coefficient, we use this modified coefficient, but mere use of this modified coefficient will not allow the front to move from left to right. For that, I must have either this has to be accounted, the moving coordinate system, or the original equation, you have to have the convective term, that is u del c del x, that term has to be there, which we in one of those derivations where reaction is involved, we introduced dl as well as that u del c del x. So that the purpose of that is, unless you provide that term, the front will not move. Okay, or you can work with the final equation that you have for static system and remove that z by z minus u bar t, use the moving coordinate system. Now there is a concern, this u bar should be what in case of porous medium? Obviously this u bar has to be, in case of porous medium, we are looking at the average velocity. Okay, so average velocity through the pore. Okay, so the average velocity through the pore, these would be same as the interstitial velocity inside the porous medium, because superficial velocity takes into account something else. So these u bar, when we write that in the error function term, this u bar has to be the interstitial velocity. Okay, so that is that one thing we must keep in mind. For that matter, this V is also the, I mean, though I am writing it as a V, it is U bar. Okay, so if I use U bar, then it is the same term you have to use. Okay, so this is what we had done. Let me check. I do not have anything here. So let me go back to the share screen option once again. The other question was regarding this shear stress, the definition of tau. Uh, First of all, when I work with this capillary, you must make note. I mean, this is in the context of pressure drop. So in the context of pressure drop, if I have this as the let us say I call this what? I call this z-axis, and this as the radial direction. Okay, so we note here that when I mean, if I just simply considering, if I'm considering the flow in a capillary, laminar flow in a capillary, so velocity at the wall is 0, velocity at the wall is little bit more here, one layer is sliding against the other, maximum at the center, then again it decreases all the way to 0 at the wall. Okay, so we note here that r is in this direction. Basically it can be, you can consider this also r is the radial direction. So we can see that it is maximum, velocity is maximum at r equal to 0, and velocity decreases as r increases. So we note here that du dr in this case is negative. Du dr is negative. So this you must keep in mind. And when it comes to the tau, definition of tau, you may recall that I have mentioned tau rx in that derivation. So tau rx means r is the plane on which the shear stress acts, the direction of the plane on which the shear stress acts, and x is the direction, the actual direction in which the shear stress is acting. Right. So plane on which the direction on which the shear stress acts means if I have a layer, let us say this is the layer, and this layer is acting on this plane. So this plane, this layer is applying a shear stress on the plane below. Now this plane will have a direction. That direction is normal to this. So this would be the normal direction n hat, which happen to be in negative r direction. Okay, so the plane on which the shear stress is acting, that will have a direction which is in negative r direction, because any area will have a magnitude and a direction, since it's a vector, and that is what is the direction. And x or tau rz in this case, let us say, I think we used x in case of pressure drop, discussion of pressure drop. So let us say I call this x. So this has to be x if I go by the dispersion, but anyway, dispersion is over. So now this tau rx, so it is acting, the shear stress is acting in x direction and acting on a plane which itself has a direction which happens to be on negative r direction. And this shear stress, if it is acting on a plane, and I mean the shear stress, if it is acting on a plane, when shear stress is positive, it acts on a positive face in a positive direction, or it acts on a negative face on negative direction. Okay, so what we are doing here is tau rx, you have to remember the sign of tau rx accordingly. So you may notice that I have picked up, I mean, if I make this profile bigger, if this is the profile, I have picked up an annular element. I have picked up an annular element. So annular element means a ring shaped element. So on this side I have, if I take the front view like this, so then this is the annular element. This is the annular element. Okay, if I look at the side view here, it would be a ring like this. Annular element is like this. So now I'm focusing on this part. I'm picking up a differential element here, and then I'm trying to find out the tau is acting. So upper plate is imposing a shear stress on the lower plane in this direction. Whereas in this case, that this layer is having a higher velocity compared to this layer. So here in this case, this plane is imposing a shear stress back in this direction. So you can see that when I have drawn that in the presentation, tau rx at r plus delta r and tau rx at r. So this is in this direction and this is in this direction. One should not confuse with the situation where I do not consider a ring, rather I consider an entire circular cross section. In some of the books, you may see that this part is not there. This part is not there. So you are looking at a circular cross section. So in this case, so the tau on this side and tau on this side both will act in the same direction. But I am not talking about that. I am talking about an annular element. Okay. I am talking about an annular element like this. And I'm talking about the stress at this point and stress at this point, not stress at that point. So that's why they are in two different directions. Okay. So this is one point I must make note of. The other point is that in some places, while applying Bernoulli's equation, I have used u square by 2, and I have not divided it by g. It is, I mean, you can divide, if you divide it by g, then you have to divide all the terms by g, or you do not divide any term by g. I mean, so this has to be consistent. So if you do not do not divide by g, the unit would be different. Okay, individual terms of Bernoulli's equation will be different. But you have to be consistent. Either you do it on all terms or you don't do on any term. So that's the logic. Okay, so that is one thing. What other questions I have? Let me see quickly. The other question that I have here is shear stress gradient. When I'm having a flow through a capillary, the shear stress gradient at the center, the shear stress would be 0, and shear stress would be maximum at the wall. Yes. Regarding this tracer test, uh, I think there was a question on. Let me share. While calculating tracer test using a step change in tracer concentration, following tracer response was obtained under no leak off case. In this case, Q1 signifies, volume of fracture. So you have answered volume of dead zone, if any, in the system. So that is not correct. Q1 represents volume of fracture, and Q, the area under the curve, represents the total volume of the core. So let me then go back. So what we are getting is a tracer response which looks like this. This is the concentration. Let us say a normalized scale, it is between 0 to 1. So we see that when there is a fracture or when there is a crack on the porous medium, we see that breakthrough would be immediate, and then it is taking a long time to reach the concentration of 1 at the outlet. So then this breakthrough is occurring because of what? Let us say I have a porous medium which looks like this. Let us say I have a cross section, and then this is a porous block, and I have a crack running through this. So then when I change the constant, the crack running through these or a fracture running through these means it has a very high permeability. So as soon as I start injecting, so I'm having a flow of 0 concentration, and then I'm injecting, I'm giving a steep change of concentration from 0 to 1. So that front will immediately travel through these fracture with no leak off. No leak off means I'm not expecting any fluid to undergo any move any pressure driven flow in this direction. Okay, so the fluid will travel through these, and then within a very short time you will see that if the change of concentration would be reflected at the outlet. Okay, so then the moment it is reflected the outlet, I will see the buildup of concentration. Only problem is, though it is reflected, it will not be immediately, it will not reach 1. It will take a long time, because as it travels through this pathway, there is a huge area sitting here which is either stagnant zone, because I assume that that is not leaking, fluid is not leaking into this area. So a stagnant zone is sitting there. So stagnant zone means this is open for diffusion. The porous medium means there are pathways available. So through them, there is diffusion happening. So as the 1% concentration travels, little bit will undergo molecular diffusion through these pores, through these porous network. So by the time it reaches here, it will not be perfectly 1, it will be less than 1. This is one way. And second thing is, you can expect a very slow amount of movement of the concentration front, which is probably several orders of magnitude slower than what the movement we have seen through the crack, because crack, it'll travel immediately, whereas a very slow movement through this porous part you can expect. So if there is a movement, so that will also contribute a little bit at the outlet. So you will find that there would be a breakthrough immediately, and the breakthrough would be caused by the flow through these crack. And so if this is the cumulative flow, if x-axis is the cumulative flow, then these volume represents the volume of this crack. I mean, it can give you an estimate of the volume of this crack. Whereas when we look at the area under the curve here, this area under the curve, these will give you, because it will reach 1 when this entire block is at 1% concentration. Then only, otherwise it will continue to show up at a lower concentration. So this will asymptotically, it will reach value of 1. So if we look at this area under the curve, that will give me the volume of this entire porous medium, because this entire porous medium has to be I mean, it is diffusing, right? So as it is diffusing, the concentration within the pores, that is increasing from 0 to maybe 0.01, 0.02, 0.03, like this, as time progresses. And at one point you will find at the outlet it has reached 1. So at that point, you know that this entire porous medium, simply by diffusion and little bit by through this flow, you have completely filled this porous medium with the concentration that you have injected. Okay, so that is why the area under the curve will give you the area under the curve will give you the total volume that belongs to this block. Okay. In fact, these volume, when it comes to volume of the fracture, you are looking at this area of the curve. This area, if you are looking at, so that means 1 multiplied by this, so that area is the volume of the fracture, and this remaining area that I have would be gives me the volume of the porous medium part, porous part. Okay, so this is the crack and this is the porous part. Total is complete this one. Okay, so I believe I am going to stop this discussion here itself. I request my TAs if they have any other comment or anything at this time. Shruti, please confirm whether it is all right. I should stop the session now. Thank you, Arindam. Shruti, is there any question or anything at this time? Okay, so in that case, all the participants, I hope you are following this course all right, and keep asking questions, so that I get an opportunity to elaborate further on any other topics that you or any other issues that comes up. And all the best. Over to the NPTEL coordinator. Over to the session coordinator. Yes. Thank you.
Thank you, sir.
So I leave now.